Hello Year 10s, this is lesson 7 in the 1.3 booklet, Making Use of Energy. I'm just going to recap what we saw in the last lesson. Both of these cans were filled with water to the same volume. Why did the silver can remain cooler? Well, the reason is with the black can, the heat source gives off heat waves, infrared heat waves in all direction. So some to the left, some to the right. Equal amount hit both cans. The black can absorbs the vast majority of the infrared heat waves, and then they pass through the can by a process of conduction, that's heat transfer in a solid, and it heats up the water inside, and the water heats up by convection currents. Hot water rises, cool water drops, and the whole can gets warmer and warmer and warmer. Now in the silver can, yes, the same number of heat waves strike the silver can. Some are absorbed, but quite a few of the infrared heat waves are reflected off. They never get to heat up the water inside, so the water doesn't heat up to the same degree as in a black can. Now, today what we're going to look at is which colour is the best at emitting or giving off heat waves. And I want you to make a prediction now. We're going to be looking at 4 colours. And those 4 colours are silver, shiny black, white, and matte black. Matte is like a dull colour. It doesn't reflect light. So I want you to think, which colour is going to give off the most amount of heat? So say, for example, we had 4 bags. A shiny black bag, a white bag, a silver coloured bag, and a matte black bag. If you were to put hot water into each bag, which bag's water would cool down the quickest? Which bag will give off, which one would emit the most amount of infrared heat waves because of it's holding hot water? So number 1 will be the one that you think that gives off the most amount of heat, so it will cool down the quickest. Whereas number 4, you're thinking, right, this colour bag is not going to allow very much heat waves to escape, and so it's going to keep the warm water warmer for longer. So don't be afraid to get the wrong answer here. Just go with what your gut thinks. Now, we can test which colour emits the most amount of infrared heat waves using something called a Leslie's cube. Let's have a quick look at a video first on the Leslie's cube. So a Leslie's cube is a metal box with a bung in the top. You can see the person's hand holding the bung. We can take the bung off and add in some hot water. Now, the face that you are seeing from the Leslie's cube at the moment is the silver colour. Silver, white, black, shiny black, and that is matte black, is dull. funnel in, hot water in. Lots of hot water in. Bung in. Now I'm just pausing the video for a second. The hot water is going to heat up the inside of that Leslie's cube. The particles on the inside walls of this metal container are going to start to vibrate, and they're going to pass on those vibrations to adjacent particles, the next door neighbor particles. And so they're going to heat up, and eventually the particles are going to vibrate on the outer surface of the metal cube, the Leslie's cube. So heat has been transferred from the water through to the outside of this metal tin by a process of conduction. Now what happens mostly is infrared heat waves are emitted from the outer surface of the Leslie's cube. Let's play the video a bit longer. Now we've got an infrared digital thermometer, and we can take readings of the infrared heat waves being given off or emitted from all four sides of the Leslie's cube. How many infrared waves are emitted, given off from the white side? Now, how many infrared heat waves are being emitted from the silver side? And then from both black sides of the Leslie's cube. So we have here a bird's eye view of the Leslie's cube. This side, silver. This side, white. This side, matte black. And this side is the shiny, no-e, shiny black. Now, these are the values for the amount of infrared waves that are emitted. The matte black was the most, 67 degrees, closely followed by the shiny black, 65 degrees. The white, 57 degrees. And believe it or not, the silver side emitted the least amount of infrared heat waves. That was a quite cool 32 degrees C. These results may surprise you. The matte black emits the most amount of heat waves, and so anything dressed in matte black will cool down very quickly. So not only does black absorb the most amount of infrared heat radiation, black also emits the most amount of heat radiation. Most heat radiation emitted, matte black. Least amount of heat radiated, silver. And then 2 and 3, that will be shiny, no-e, shiny black number 2, followed by white. Now, you might be thinking to yourself, why is it that matte surfaces lose more heat radiation than shiny surfaces? Well, if you were to look under a microscope at a shiny surface, it's quite smooth. Whereas a matte, dull surface has a big surface area. Think about that as a piece of string. If you were to pull that piece of string from here to here, it would be out here somewhere. Massive surface area, so it can emit huge amounts of heat waves from its surface. So that's the answer. Matte surfaces have a large surface area, so they can emit large amounts of infrared heat waves, causing the surface to cool down the quickest. Okay, here's an exam style question. A householder monitored how air temperature inside his house changed over a 2-hour period. 2-hour period. The householder measured the temperature every 15 minutes. 7 o'clock, 7:15, 7:30, 7:45, 8, and so on. And figure 10 shows how the temperature changed. The householders using a digital thermometer, what would be an appropriate resolution for the digital thermometer? Well, what's the smallest temperature change it can measure? And if we look at these two here, that's 22, that's 22.5. This one is 21, this is 20.5. Its resolution, the smallest number that it can measure to, is 0.5 degrees C. The householder's results are shown by a line graph in figure 10. Why wouldn't you plot it as a bar chart? Well, time in hours and air temperature are variables that are both continuous data, so it's a line graph. Keeping heat in at home. For most of the year, you want to keep the heat in for two main reasons. Number one, to keep warm. And number two, to save money. And number three, reduce your carbon footprint, save the planet. Now, where does the heat go? 10% escapes through the windows, 15% through the floors, 15% through the drafts. The walls have a big surface area. 35% moves through the walls and 25% of the heat escapes through the roof. On average. Question 1. The house above loses 760 joules per second of heat energy to the surroundings. Calculate the rate of heat loss via the walls in joules per second. Well, 760 is 100%, but the walls are only 35%. So, multiply that by 35 divided by 100 and you'll get your answer in joules per second. Last thing, Draw your own house or a house you would like to live in and add in the heat loss arrows with their percentages. I'm going to draw my house now. So there's my house. With a 5-bar gate to the right hand side and a couple of trees. They're not mine, mature trees, lovely. And now all you have to do is add the heat arrow losses. 25% through the roof. 10% through windows. 15% through the floor. Drafts, gaps. Drafts, 15%. And finally, the walls, a big one, 35%. Okay, that'll do for this lesson. Well done.